All right, so this one is going to be 15.5, the directional derivative. And the gradient. Okay, so we were talking about, in the early parts of this chapter, we were talking about two variable functions. We could take partial derivatives in the x direction, dx, f. We can take partial derivatives in the y direction. And those partial derivatives tell you how your function changes as you move in the x direction or in the y direction from any point. All right. So I guess I've drawn, what's happening at the origin, but you could do this anywhere. Okay, sorry, that's a df dy. Okay, so the big question though was, what about the change in f in all these other directions, the infinite many other directions? How does f change, right? If we only have the partials, it's only two specific directions. Okay, so we're going to answer this question in this section, but of course only for differentiable functions. All right. We're not going to, as we said before, we're not going to really work with non-differentiable functions. Those functions can behave extremely wildly, but you'll see when functions are differentiable, things work out very, very nice work out very nice and smooth. Okay, so remember, to be differentiable means that f of x, in terms of its derivatives, behaves like its linear approximation. All right, and from that, we got the fact that the chain rule works, right? So differentiable tells me that, let me write this down. Differentiable is equivalent to linear approximation works, right? Which meant that chain rule works, or which gave us our chain rule formulas. Okay, so these chain rule formulas are going to be one way to see why derivatives of f in these other directions are so easy to compute. Okay, so why is that? Well, the way we're going to think about derivatives in other directions is like this. So we got x, we got y, we got z. Let's say we've got our function graph above here. Let's say we're interested in this point right here. And above that, this is the location of that point. Okay. Let's say, let me draw the kind of x and y directions. So this is the x direction, that's the y direction, but we're not interested in those two directions. We're interested in something like maybe that direction. Or, let me do something more like that. All right. So the question is, how does f change in that direction? Well, one way we can understand this change that's actually workable is to draw a curve here whose tangent at the point of interest is the direction that we want. All right. Okay, so I'm going to call that curve r of t. Okay, what we can do is we can go up, right, along the curve, do the composition of the function with the curve, right, the function after the curve, and we'll see one variable function that we basically exactly what we talked about in the previous sections. Okay, so this composition, as we said in the previous sections, f of r of t, is a one variable function. I guess, again, this idea of writing it as a vector valued function is not really that natural. I am going to often do it just because we learned of, this motion business through the vector valued functions, but I think I'm going to try to keep it like f of x of t, y of t as much as possible. All right, so again here, r of t equals x of t comma y of t. Okay, so this guy here is a one variable function, and we can calculate its derivative, which is what we did last section, d dt of f of x of t comma y of t. So this is very, very doable. We saw last section, you just use a chain rule, or even if you only knew one variable calculus, you could just convert everything to one variable calculus and take the derivative. All right, so the point is this thing is very, very computable. Okay, so let me label that as easy, right? Easy as in we understand this completely. All right, now why would we want to do that? Well, that represents, this change down here actually represents how the function changes, because if we go from our original t, right, to the curve and then upwards, right, then we have a function, we're kind of porting this function backwards to t, right? So the function maybe looks something like that, right? When we pull it backwards. In fact, technically in math, you call this a pullback, right? And what I mean is, what would the values of this curve be upstairs? Well, if I take any point t, I would push it to the position on this curve on the other side. I would go all the way up until I hit the graph. That height would be the value of t up here. Okay, so this curve over here mirrors pretty well what's going on with the function in the direction that we're interested in, this specific direction right there. All right, because the curve has the direction, has the correct velocity vector at the point of interest. Okay, so the derivative of my curve at the point of interest should give me very good information about how my two variable function changes as I move in that direction. And in fact, it does. That's pretty much what we want. Pretty much what we're looking for, except for one major thing, and that's that what happens if we know that we can do many different parameterizations of the same curve. That's one issue to worry about. Another issue to worry about is we know we can do many different curves that have the same tangent vector at the point of interest, right? So, for example, let me just draw the domain of our function, right? And let's say here's our point of interest. We want to know how f is changing as it moves in that direction in the domain. So our discussion that we just had, I said we could just take a curve whose velocity vector is in that direction, exactly in that, well, its velocity vector is exactly this vector, this red vector that we're looking for, right? But not only can we parameterize this guy in many different ways, we can also draw many different curves that pass through the same point with the exact same velocity vector. All right. So there's this issue of, if I do a different curve, am I going to actually get the same answer for what I'm looking for, right? Because this derivative here, right, this one variable derivative here, is supposed to represent how my function changes. And if I do different curves and I get different answers, then that's not going to be any good, right? So we're going to resolve the issue. We're going to resolve one of the issues right now. So one issue is that even if we just do one curve, right, we just say, all right, I'm never going to parameterize, I'm never going to do this idea by using parameterizations with, these horrible looking curves. I'm always going to do a line, right? I'm always going to parameterize this direction, or parameterize with the correct velocity vector, I'm always going to do it in this direction using just a line. All right. Well, it's still no good, possibly, because we can parameterize a line so that it moves at different speeds, right? And if you move at different speeds, then this function over here, this kind of pullback function that we talked about, is going to look different, right? For example, if I'm here, right, and I have this height, if my t is moving really, if my parameterization in terms of motion, let's say, is moving really fast, right? So maybe just one step here corresponds to a huge step down here, right, on my curve, then it's going to look like my function changes really fast, right? On the other hand, if one step here corresponds to a tiny step on the curve, then it's going to look like my function changes really slowly. Okay, so I'm going to lose information if I kind of do different, or I'm going to get different information if I do different parameterizations. Now, of course, if my function is increasing, no matter what, I'm going to get a positive derivative down here. And if it's decreasing, I'm going to get a negative derivative. But the number that derivative is going to change depending on my parameterization. So what I want to do, first of all, is to say, okay, when I talk about figuring out how a function changes in a certain direction, I'm going to insist that I'm going to use unit vectors to represent that direction. All right. So I'm interested here, right? This is the ddx. This is the x direction. That's the y direction, right? If I want to know what's going on in this direction here, I'm going to always do my parameterizations so that the velocity vector at the point of interest is 1. All right. In other words, this guy has to be a unit vector. Okay. And at this point, let me start giving this guy a name because we're going to be writing down some notations in one sec. So let me call it U. All right. Okay. By the way, first of all, notice that this corresponds very well with what's going on when we talk about ddx, df dx, and df dy, because those are moving. Df dx would be how f changes as you move to the right. But because we're doing df dx, just a native variable x, that's moving, kind of with unit speed to the right. And then same idea with df dy. Okay, so we're always going to insist that we use unit vectors. All right, at least that's how our book discusses this topic. But it's perfectly fine. In general, you can define a more generalized idea of a derivative where you don't insist it's a unit vector. But in that case, you just have to remember that, remember how long the vector is that you're working with, all right? Okay, so at this point, we can write down some notation. So d sub u f, this is called a directional derivative of f in the direction u. Right? And u has to be unit. Okay, so this represents how f changes as we move in the u direction at whatever point we're plugging in, right? So normally, of course, d sub u f is a two-variable function because we can calculate it at any point in the plane. And so we're talking about how f changes as we move in the u direction at that particular point. Okay, and what is that? That's exactly ddt f of x of t, y of t, where x of t, y of t is a parameterization of that passes through our point of interest with velocity vector exactly u at that point. All right. So I guess I wrote down a general thing. So let me fill in what happens, if you have if you're actually calculating at a point. So d sub uf at AB, right? This would be d dt f of x of t, y of t at t naught, where x of t naught is equal to a, y of t naught is equal to b. Okay, so that's what you would do if you actually wanted to compute at a specific point. All right, and again, it accurately represents how your function changes, all the way up here, how your function changes as you move in the direction t. So in this case, right, our function is changing. Looks like maybe it's the derivative is directional derivative perhaps is negative, right, where this is kind of the zero direction, all right, or zero level. Okay, and because we're doing a unit vector, right, it's kind of in a way accurate in that one step here corresponds to one step along your curve, right, roughly, right, at that point. Okay, it doesn't have to be, so that sounds like it's kind of like an arc length parameterization, but you don't really need an arc length parameterization. You only need this to be happening at the point of interest. Okay. All right, but that's kind of the idea. All right, now, again, we said that there is some issue, right? Because if my arrow is pointing in that direction, what if I use two different parameterizations that have the same velocity at the point of interest, right? But two different parameterizations. Will I get two different answers for this guy here? And if I do get two different answers, then that means the directional derivative, the way we've defined it, is no good. Okay? Because there's an ambiguity there. But because, one, we're assuming our function is differentiable, that means the chain rule works. And because the chain rule works, we can actually continue our computation. So let me continue this down to here, right? What is this derivative? This is df dx, right? And then dx dt plus df dy, and then dy dt. Okay, and let me again put in red where we're evaluating these. So this is at our point of interest, AB. Okay, this is at t equals t naught, right? The point that corresponds to a comma b under the parameterization of my curve. This is at a comma b, and this is at t equals t naught. Okay. All right. So the chain rule works, again, because we're differentiable. If we weren't differentiable, this line would fail, all right? And the whole thing falls apart. Okay, now, how does this tell me that it doesn't matter what parameterization I use? Well, this term right here, df dx, is independent of the parameterization, right? There's no mention of the parameterization in this term, right? It's just a partial derivative in the direction x. Right? Completely independent of parameterization. This guy here is independent of the parameterization. Same idea, it's df dy. Okay? All right, so those two terms aren't giving us any trouble, but what about the other two? dx dt, right? That depends on the parameterization. dy dt, that depends on the parameterization, right? But not really, because we insisted that at our point of interest, t equals t naught, right? Or the corresponding point in space a comma b, we insisted that this red arrow, that arrow be a unit vector, right, in our direction of interest, u. Okay, so this guy here, dx dt and dy dt, is actually u, right? So u is equal to dx dt, dx dt, I plus dy dtj. All right, and again, this is happening at our point of interest. Okay, right? That's what we said in our definition up here, right? Parameterization that passes through our point of interest with velocity vector exactly u, where u is a unit vector, right? Where it's not just in that direction. It not only has to be in the same direction as u, it has to be exactly the unit vector in that direction. And so there's no ambiguity as to what dx dt and dy dt are. They're exactly u, and u is a unit vector. Okay. So if I do a different parameterization, maybe this parameterization represented by the yellow curve here, I'm going to get df dx, dx dt, df dy, dy dt. And the terms are going to be literally the same numbers as if I did the blue parameterization, right? Again, df dx would be the same, df dy would be the same, dx dt, dy dt, right? Put them together, they would be u. And then for the yellow vector or the blue vector, both of those would be u. Okay, so no matter what parameterization I use to represent, to in a way represent this direction, I get the same answer. Okay, so that's kind of actually somewhat surprising perhaps, because you maybe would believe that the fact that, for example, this yellow curve curves in one direction, whereas the blue curve curves in the opposite direction, maybe that would affect this one variable derivative up here. But in fact, it doesn't, right? Because of the chain rule. Okay, so either of these two parameterizations will give me the same answer. And so what that means ultimately is that the directional derivative is well defined. All right, there's no ambiguity as to how to compute the directional derivative. Okay, because no matter how you try to do it, with whatever parameterization you choose, you're going to get the same answer, as long as, of course, you follow the condition that you're using the same direction and you're using the length should be 1. Okay, so in other words, length of u equals 1. Okay, so of course, in practice, right, if we're interested in this point, we want to know how the function changes in that direction. In practice, probably if we were to calculate the directional derivative from the definition that I just described, in practice, probably the easiest parameterization is just to use a straight line parameterization of the correct velocity, right, with a constant velocity in that direction of this length. Okay. Again, it doesn't have to be constant velocity anywhere else. Like over here, it doesn't matter. But just the most convenient thing would just be to use a line of constant speed. Okay. And you might think, why didn't I just define it like that from the very beginning, right? Why not just always use lines? Well, in the future, you might want to talk about functions defined on a surface, right? So I have a curved surface here. Let's say I have a function that's only defined on this surface, right? Let's say, for example, you have a sheet of metal, right? Just a curved sheet of metal. And let's say it's hot, right? And you want to know its temperature, or you're considering its temperature at different locations. What is that? That's a function, right? At this point, there's a temperature. At this point, it has a certain temperature. At that point, it has a certain temperature. So this is a function. The function is defined on a curved surface, right? Not on a plane, on a curved surface. And so if you want to think about how the temperature changes, right? Let's say we're interested in this particular point right there. How does the temperature change as you move in this direction, let's say, right? Then you can't just use a straight line to do any calculations, because a straight line doesn't even stay on the surface, right? Because the surface is curved, right? The surface perhaps, if I were to do kind of like a profile, the surface may be curved downwards like that, right? And so you wouldn't be able to use straight line to do any sort of derivative calculations or anything like that. So you would have to use something curved. And so that's where our idea of directional derivative is able to accommodate this fact. All right. Okay, so this is a curved sheet of metal, but maybe you think, who cares about that? But you can do the same example with the Earth, the surface of the Earth, right? You're calculating change of temperature at this particular location on Earth, right? And maybe perhaps in this direction. Well, you can't do a straight line because, again, a straight line obviously, right, is going to be tangent to this sphere, and so it's not even going to touch my Earth, and so my function isn't even defined on this blue line. So I have to use a curve, right, to understand the derivative. Okay, so that was the reason why we defined the directional derivative so generally. Okay, so let's do one calculation, and then we'll talk about something really nice. So let's say f of x comma y is equal to, again, just something simple, x squared y cubed, right? Let's say we're interested in the point, so how does f change in the direction, let's say, let's do something that's not too hard to compute. So let's say in the direction 1 comma 1, all right? At, I should have a point, right? At 3 comma 2, okay? All right, so we're looking, if this is our domain, we're at 1, 2, 3, 1, 2, we're right there. We want to know how our function changes as we kind of move in that direction, okay? All right, so the first thing is, this guy is not a unit vector, right? So we want to talk about directional derivative for this class, for our book. We insist that the direction is represented by a unit vector. So we need to convert this guy to a unit vector. So the unit vector, we're going to call it u, is going to be, well, just this vector divided by its length. The length of this vector, 1 comma 1, is root 2. And so the vector that we actually want to work with is 1 over root 2, comma 1 over root 2. All right. Okay, so the directional derivative in the direction u of f at 3 comma 2 is going to be, well, let's do a parametrization. Or not. Let's not, right? We think we might have to because everything I talked about in terms of derivative has something to do with parameterization. But let's write out the formula. Even before we do a parameterization, let's write out the formula again. df dx, dx dt, plus df dy, dy dt, right? This was happening, df dx was happening at 3 comma 2, our point of interest up here. df dy was happening at 3 comma 2, right? dx dt, dy dt, what are they? Well, doesn't matter what the parameterization is because we already know these two guys together, right? U is equal to dx dt I plus dy dt j, right? That's literally the direction vector u, right? From our definition. And so we actually don't need to do a parameterization. So that's one of the great things here, right? So this is actually just equal to df dx. Our function was x squared y cubed. Let me write down our function in the corner here. All right, so df dx is 2xy cubed, right? df dy is 3x squared y squared. Okay, dx dt is the x component of u. dy dt is the y component of u. U was 1 over root 2. The x component was 1 over root 2. The y component was 1 over root 2. So no matter what we do with our parameterization, we're going to get this answer if we did it correctly, right? Okay. And I guess I should emphasize, right? All of this x and y, this is, let me do it like this, evaluated at 3 comma 2. This is evaluated at 3 comma 2. And let me write all that out. So this is going to ultimately be equal to 2 times 3 times 8 over root 2 plus 3 times 9 times 4 all over root 2, all right? Whatever number that is. One thing we can see, it's a positive number, so it means our function is increasing. at 3, 2. Okay, how fast is it increasing? Well, just like in one variable calculus, that number, the magnitude of that number tells me how fast it's increasing. Okay. All right, so if it's a big number, it's very steep, right, as we move in this direction. If it's a small number, it's increasing but not very fast. All right. Okay, if you think of your function as a as describing the height, the elevation of a hill, right? Given a position on the map, so that's where the xy come in. Then if the derivative is positive, that means we're going uphill as we move in this direction, u. And if it's a very big number and positive, it means we're walking very steeply uphill, for example. Okay, if it's a small number and positive, then it's not very steep. The hill's not very steep. If it's negative, we're going downhill. If it's a very big, very negative number, it's very, going downhill really fast. All right, maybe like a cliff or something like that. Okay, so you can see that despite all our talk about parameterizations and stuff, ultimately when we do our calculations, we don't need any parameterizations, right? And the only reason, again, that works is because our function is differentiable. All right, so you can imagine if you're working with non-differentiable functions and you're trying to understand how that function changes, it's going to be a huge problem. All right. Okay, so let me write out this this directional derivative again, and let me reorganize the terms just a little bit, and then we'll have something really important. Okay, so again, f of x comma y. I'm taking a directional derivative of f in a certain direction u. What is that? That's df dx. dx dt. Oh, sorry. At this point, I'm going to stop writing the dx dt because we know by now the parameterization doesn't matter. So I'm just going to write down, let me write down the coordinates of u. So this is, let's say u is equal to ai plus bj. All right. Then df dx, we're going to have df dx, and then we already know at this point this is just going to be a, plus df dy, and this is just going to be b. All right. Again, the chain rule tells me this should be dx dt, but we already know that dx dt is a. This should be dy dt, but we already know that should be b. Okay. Now here's the reorganization. I'm going to write this as df dxi plus df dyj dot product with ai plus bj. Okay. Nothing really happened here because when we take the dot product, we have that times that, which is the first term, and that times that, which is the second term. Okay, so nothing really fancy happened. However, notice that this is equal to df dx I. The first term, I'm just going to leave it for now. Dot u. Okay, so directional derivative is actually just df dxi plus df dyj, and then dot the direction that I'm interested in. Okay, no matter what direction, right? So if right now I wanted to figure out how the function changes in this direction, then I could do this computation, right? I calculate df dx, df dy, and I dot the, I put that into a vector. I dot u, that's my answer. Now, if I decide, in a couple minutes I want to do that direction instead, I can use the same df dx and the same df dy, but instead I would dot the different vector. So my initial vector is v, now u, now it's v. I would just dot v instead of u. Okay, so this guy here on the left side is always going to be the same, same value or the same vector as long as you're at the same point. Okay, so that's super convenient, right? So if I want directional derivative in any direction, essentially all the information is encoded in this vector right there. right? Because to get the actual specific derivative, I just dot it with the vector that represents the direction of interest. Okay. All right. Oh, by the way, notice that the directional derivative, just a small thing to note here, directional derivative in the direction I is going to be df dx. And the directional derivative in the direction j is just going to be df dy, right? Because in the direction I, if you write I is just I plus 0j, right? So when you dot it with this special vector that I've put a box around, I'm just going to pop out only the df dx. The df dy goes away. Same with df dy, directional derivative in the j direction. So that's a really important, it's kind of a small thing, but it's important to note that the directional derivative plays very well with the idea of the partial derivative. Okay? They're compatible when you're talking about change of f in the x direction or in the y direction. The two concepts of derivative are compatible. Okay, in any case, this one special guy is, we've seen, it's so special that we give it a name, gradient f. Gradient of f, I guess, technically, but usually we just say gradient f. All right, so this is equal to df dx I plus df dy j. Okay, so this is what we're going to call in the future, in maybe 3 weeks or so. We'll call this guy a vector field, because it's actually something that at any point in the plane, the output is a vector, right? Because we can calculate this quantity on the right hand side at any point x and y, x or y, right? For example, if we wanted the directional derivative here, we would use these coordinates, whatever, 4, 2. If we wanted to calculate the directional derivative there, we would use these coordinates, -2, 3. All right. So this gradient f quantity actually is not just a vector, but it's something where every point on your plane has a vector associated to it, right? And that vector is df dx I plus df dy j, evaluated at your particular point. Okay, so in particular, let's if we had a function, perhaps gradient f would be pointing in that direction here, gradient f might be pointing in that direction here, it might be pointing in that direction here, and that direction here. It could be 0 right there, perfectly legal. The 0 vector is a perfectly legal thing. And maybe a gradient f is pointing in that direction there. Okay. So again, at every point in the plane, we have a vector. And that's exactly what we call a vector field, or what we will be calling a vector field in the future. This is probably the most important vector field that we're going to be working with in this class. But we'll see there's lots of different interesting vector fields. Okay, so we call this guy the gradient, and now we can write down a kind of a short version of what the directional derivative is. So how f changes in the u direction is equal to gradient f dot u. Okay, and again, I've written this kind of in an abbreviated way, but technically you should be writing at this particular point and at this particular point. All right. Okay, so ultimately, after all this discussion from 15.1 to 15.3 to 15.4, we finally have a nice, super simple way to understand how a function changes in a certain direction, right? In any direction, u. Okay, now, let me do a kind of calculation example, and then we'll talk about this gradient a little more closely. Okay, so for example, f of x comma y equals x sine y, right? What's gradient f? It's equal to, let me write down definition, I plus df dy j. That's equal to df dx is sine y, I, And then df dy is x cosine y j. All right. Okay, so this is the gradient of f, and again you can see that it depends on x and y, right? So at every different point on the plane, we're gonna have a different vector representing which is the gradient at that point. Okay. All right. So in particular, if I want to do gradient f, if I wanted to do the directional derivative of whatever direction, right? 1 over root 2, comma 1 over root 2, right? Again, this is a unit vector here, right? What is this? Super easy, right? I used the gradient that I just discovered, sine y, x cosine y. Let me plug in the actual values of my point. Oops. There we go. I should actually put in a point, right? At 1 comma 2. That's equal to sine of 2 times 1 over root 2 plus x cosine y is 1 times cos 2 times 1 over root 2. That's it. All right. And if I change my mind, instead I want 3 over 2, comma 1 half, right? I want to understand how my function changes here. Then it would just be sine of 2, root 3 over 2, plus cosine of 2, 1 half. Okay. So the gradient, once we have the gradient, the directional derivative is super easy to compute. Okay, so let's look at this gradient. Seems like it should be very important. So again, duf is equal to gradient f dot u. And let me just put in the point this time at AB. So let's say we're interested in what's going on at a specific point a comma b dot u, and in some direction u. So let me draw the picture. So here's A, here's B. Let's say we're interested in this direction u. Okay, let's kind of think about the gradient. So actually, let me not draw u. Let me draw a gradient of f. Let's say the gradient of f is in this direction. Okay. All right. So just from the picture, right? Let's say we've calculated gradient f. Let me emphasize this gradient f at AB only, because at different points, of course, the arrow could be pointing in different directions. It could have different lengths. Okay. So what if u were in this direction? What do we know about the directional derivative of u of the function f? Well, without even knowing any numbers, without knowing the formula for f, I can immediately tell you that the directional derivative of f in the direction u at the point AB is going to be positive. All right, so if this is u, then directional derivative u, f at AB is going to be positive. All right. Why is that? Well, the directional derivative is the dot product, right, of the gradient f, and u, right? So if you have two vectors pointing where the angle between them is less than 90 degrees, right, then the dot product is going to be positive, right? Why is that? Well, remember, that's equal to gradient f at AB, length of that, times length of u, times cos theta, where theta is the angle between the two vectors. Okay, so if the angle is less than 90 degrees, right, here's the graph of cosine, right? If the angle is less than 90 degrees, I know that cosine is positive, the length is positive, this guy here is positive, right? Because I've drawn the actual vector, it's not 0 in particular, right? So this whole thing is positive. Okay, so without any formulas or anything like that, just knowing the direction of the gradient vector, I can tell you the directional derivative in this particular direction is going to be positive. And alternatively, if I were to look in that direction, let's say v, right, then a directional derivative in a direction v, f of AB, for the exact same reason, I know that's going to be less than 0. Okay. All right. What does this mean? This means that in practice. So if we think of f again as elevation, and our plane representing where we are, right? So we're hiking in the hills or something like that, right? If I know the gradient function of my hill in a way, then I know that then in this example, right, walking in the u direction is walking uphill. Walking in a v direction is walking downhill. All right. Okay, a couple more things. So this formula, gradient f, length of gradient f times length of u times cosine theta, tells me a lot because cosine theta, I know, is always between 0 and 1, minus 1 and 1. Right? So when is d sub u f, or let me write like this. For which u, I've already used u, so let me use another letter. For which w is d sub w f as big as it can be? All right. Okay. What's the again, if we're thinking about a hill, right, and we're standing at the point AB, this is basically asking me in which direction is the hill as steep as possible, right? Just at the point where I'm standing. Okay. So again, let me emphasize that with the AB here. What is that? Well, like I said, cosine we know is between minus 1 and 1. So the biggest this expression over here can be is when cosine theta is equal to 1. All right, so it's when the angle between gradient f at AB and u is pi over 2, 90 degrees. Sorry, is 0 degrees. How many times did I say 90 degrees? Sorry, is 0 degrees. Right? In other words, same direction. We're going to talk about 90 degrees in 1 second. Same direction, right? So it's when gradient f and gradient u is in the same direction. Okay, so again, in terms of our hill example, that means that gradient f is the direction, gradient f itself points in the direction in which the hill is steepest. Okay, so gradient f points in the direction of steepest ascent. Okay. So we can see physically, in a way, the gradient of f has very important meaning. All right. Okay. Again, what was the directional derivative? Our formula was this at AB, right? Gradient f AB dot u. This was equal to length of gradient f at AB times length of u times cos theta. Okay. We asked the question for which w is the directional derivative as big as it can be. What about this? For which direction is directional derivative w f of AB as negative as it could be? Okay, and again, we look at cosine. Cosine lives between minus 1 and 1. When is cosine, as negative as it can be, is going to be when cosine is equal to minus 1, right? When is cosine theta equals minus 1? It's going to be 180 degrees, right? Pi radians. And so this is going to be theta equals pi, right? And what is that? Well, that means that I have gradient f in this direction, And my w, the direction in which the directional derivative is as negative it can be, is the exact opposite direction. Okay. So minus gradient f, right? Sorry. Minus gradient f, which is this opposite direction, is the direction of steepest descent. Okay. All right, so again, the gradient is telling us a lot of information about our function. A lot of kind of very physical, relatable information about our function. So again, if we're on a hill, right, gradient f points in the steepest way up, and minus gradient f points the steepest way down, and they're opposite directions, right? Not only do we know the directions, but they're opposite to each other. Okay. All right, this steepest descent, the direction of steepest descent, this guy is used quite a lot in real life, because one way, so we'll talk about optimization next week, and it works, the way we talk about it works perfectly fine. But in real life, if you're working in multi variables, right? F of x1, x2, x3, whatever, let's say 10 variables or more, right? The techniques we're going to talk about next week are going to be very, very unwieldy and not so easy. The computations are going to be hard. And in practice also, you don't have nice formulas, as the situation will be next week. So what happens is, if you want to find where is the minimum of f, right, how would you do this? Well, so first of all, why would you want the minimum? Because the answer is because in real life, lots of things work by finding minima, right? A lot of physics works by finding the minimum of energy or something like that. So you often want to find the minimum of something. Okay, so how do you find the minimum? Well, think of the hill problem, right? You've got a hill. Of course, this is in, let's say I'm going to draw the picture in the plane as two variable function. You want to find, let's say, the minimum point, right? On this terrain, let's say, and you're here, right? Which direction are you going to move? Let's say there's lots of trees everywhere. You can't, obviously in this picture, let me, yeah, this is fine. Obviously in this picture, that's our answer, right? But if you're standing here and there's a lot of trees in the way, right, you can't really tell, right? Where's the minimum, right? So how do you actually determine? Well, you look at which direction is the steepest possible. Let's say that one. That would be the gradient of f, and you walk in the opposite direction, minus gradient f. That's your steepest descent. Okay, and in practice, maybe what you would do is you would take 2 steps in the direction of steepest descent. Take a look at the gradient. What is the gradient there, right? Maybe the gradient is now pointing in that, or is pointing maybe in that direction, right? So now you would change your direction a little bit to move in the opposite direction, and you would go down a little bit more. And you would keep on going downwards, and the idea is eventually you'll hit a minimum. Okay, so this is actually used in practice in real life. Actually, it's used right now in AI. The problem, one way to do AI these days is to actually solve an optimization problem where you're finding the minimum of something, the minimum of the errors, right? So if your program is trying to recognize characters, right, you let it make some guesses as to what the characters are, and you have some sort of measurement of what the error is, right? Was this supposed to be an A, but you said it was a B? You have a number that represents that error that you made, and you try to minimize the error, right? That's an optimization problem. It's going to be, in general, a very large variable problem because, well, when you represent characters, when you want character image recognition, let's just go with that example. How would that be given to you as input, right? So maybe a letter would be given as these guys filled in, right? So this would be, looks like it would be the letter B, right? How many variables are there? Well, I've got 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 49 different slots where I could have a pixel light up, right? So already I'm going to have, right, a huge number of variables that this problem involves, okay? So it is going to be an optimization problem, but we're not going to be able to solve it the way we did, well, the way we will next week. And so you use this idea of steepest descent in order to try to find minima. Okay, and of course, if in the future you're hiking in the jungle and you're lost and you need to get either to the highest point of the hill you're on or the lowest point of the hill, right? Perhaps that's where the river is, then you could use this idea. Take a look at which direction is the steepest upwards or downwards, and then move in that direction for a few steps, do another evaluation, move another few steps, do another evaluation, and so on. Okay? All right. Oh, by the way, if you did want the highest point, you just go in the direction of steepest ascent, which is the gradient direction. All right. But usually these problems are seen in real life. They're often phrased as steepest descent because, again, we're often looking for minima. All right. Super hard to read that. Okay. So that's two aspects of the gradient, but actually there's more. And we'll be working with the gradient for the rest of the semester quite a lot because you can see it's so important. So here's another thing. Again, directional derivative, u, f is equal to gradient f dot u. This is equal to length of gradient f, length of u, cos theta. By the way, you would never actually calculate any directional derivative using this second formula here, right? You always calculate using the first equality up here. The second one is kind of what gives us our great approachable interpretations. Okay. All right. In any case, when is this equal to 0? Well, again, if the gradient is not 0, which it could be, right? But if it's not, then that first term is not 0. U always has length 1 unit vector. That's exactly 1. Cosine theta, when is that 0? Well, here's a graph of cosine theta, and it's going to be pi over 2. Okay, so d sub u f is equal to 0 when u is perpendicular to gradient f. Okay, so what does that mean in terms of our hill? It means kind of if you go in a direction perpendicular to the gradient, right, perpendicular to the highest, to the steepest direction of the hill, then you're in a way not changing elevation, all right, in the derivative sense. Okay, again, I say that kind of in a way carefully because you will actually be changing elevation possibly because we know we can have derivative equal to 0, but your function is still changing, right? But derivative equals 0 means there's some kind of flatness going on there in a way. Okay. So the gradient is perpendicular to, in a way, the directions where your function is not changing, in quotes. All right? Let me write that down. Gradient f is perpendicular to direction where f is not changing. All right, this one is very, very imprecise compared to what we talked about, the steepest and steepest descent or greatest ascent. All right. Okay, now this guy here is particularly important though, because think about this. We talked about level curves last time. All right, let's draw a few level curves of my function. So let's say this is a level curve. Let's say this is another level curve. I'm not even going to bother with the labeling. It's actually just the curves that I'm interested in. So let's say these are some level curves. Let's say I'm interested in what's going on right there, right? let's see. Let me fill in some level curves in between. So let's say there's some tight level curves here, and let's say here is very not very tight there. Maybe I should do some elevation just for some reference. I didn't want this to get too messy, but I guess this picture is big enough. 1, elevation 2, elevation 3, 4, 5, 6, 7. All right. Okay, so it looks like here, the way I've drawn this picture, the gradient is kind of in this direction, right? But it's hard to tell, right? Without kind of a more accurate picture. But I can actually tell you exactly where the gradient should be, because along this level curve, right, the value of my function is literally 0. The change of my function is literally 0, right? Oh no, 1, 2, I forgot to label this one as 3. So this one probably should be labeled 3, right? And then the rest of this is 4, 5, 6, 7. Perhaps like this. 4, 5, 6, 7, 8. All right. So along this level curve that I'm standing on, we're at a constant height of 3. Okay. So what that means is if I move in this direction tangent to the level curve, right, my function should be constant, 3. Okay. And so my directional derivative in that direction should be 0. All right. And so what does that mean? That means the gradient has to be perpendicular to that, right? What we set up here. Okay. So I can tell you conclusively the gradient, if my level curve actually looks like this, right, then I can tell you conclusively, well, if this is the tangent vector, then for sure that's the gradient vector. Okay. I don't have to kind of look at all these other curves around here to kind of see it by eye, right? Just knowing the level curve, I know the direction of the gradient. Okay, well, it's either this direction or the opposite direction. Without labelings, I actually can't determine that. So it's one of these two. So let's be a little careful there. All right. Depending on whether we're actually looking at, I guess, a valley or a hill, right? So I guess if the gradient were in the inner direction, we would be kind of, looks like we would be kind of moving towards a hill top in the middle. Whereas if it was the opposite direction, it looks like we would be kind of in the bowl of a valley, something like that. But again, we can't say that conclusively without any labels or anything like that. Okay, so if I, to summarize that a little bit, if I just have a picture of one level curve, right, I'm interested in this point, I know tangent is in this direction to my curve, then I know conclusively the gradient is perpendicular to that. Right? It's either in that direction or that direction. Okay. So let me write this as gradient f is perpendicular to level curves. Okay. All right. Up to now, we haven't talked about, we've kind of restricted ourselves to 2 variables. Everything up to now works in 3 variables, right? Or 4 variables or 5. In 3 variables, the gradient of f would be df dx I df dy j df dz k. Okay. And then if you want to extend more variables, you just keep on going. All right, same idea. But yeah, ddx, ddy, ddz, all corresponding to their particular coordinate entry. Okay, steepest ascent, steepest descent, literally the same idea. Okay. Now, when we talk about directions of 0 change, that's going to be a little different because, as you can imagine, or as we know, for 3 variable functions, we're not talking about level curves anymore. We're talking about level surfaces, right? And so our level surface would look something like, it would be like a surface, okay? Okay, and in that case, what's the relationship of gradient f with the level surface? It's going to be perpendicular to it. Okay. So gradient f is perpendicular to level surface. All right. Okay, so let's say I were to draw the tangent plane of this surface, then this guy would be perpendicular to it. Okay, in fact, that's going to be one big application of this fact down here, right? If we need to find the tangent plane of a surface, one technique is to discover a function that has this surface as one of its level surfaces. It doesn't matter which one, right? It could be the 0 level surface, it could be the 10 level surface, doesn't matter, right? So the surface of interest is a level surface of some function that I need to discover. But once I've discovered that function, I take the gradient of it and I get the normal direction at any point on my surface. Okay. All right, so that's actually super, super useful. In fact, if you think about the last paper homework, the extra credit, I wanted you to find the tangent direction on the curve y equals x squared using parameterization. And then once you found the tangent direction, that allowed you to get the normal direction, right? And the normal direction you used in that extra credit problem to do stuff. Okay, but now that we know all this gradient stuff, we can actually find that normal direction in a way directly without having to go to the tangent, because we can discover a function whose that has one level curve being this guy right here, right? And the most convenient function we could use is perhaps just something like this, right? What's the 0 level curve? 0 level curve is, so we talked about this in one of the earlier lectures. The 0 level curve is, well, it's when f is 0. So 0 equals y minus x squared. So it's going to be y equals x squared, which is our curve. All right, so that's how you go through this procedure. You have a curve, you want to study it, right? You want to find the normal directions. You discover you make up a new function, so that the curve of interest is a level curve of that function. All right. Now, if I want the normal directions, I just calculate gradient f, right? So gradient f is, so f is y minus x squared. So gradient f is going to be minus 2x I plus j. Okay. All right. So that tells me if I'm at the point, let's say a comma b here, right? Or let me actually do a real point. So let's say I'm at the point 3 comma 9, right? Then what's this vector right there, or the opposite direction? Again, you have to kind of think about which direction your gradient points in. But in either case, right, they're both normal to the curve. So what would the normal direction be? Well, the answer is instantaneous. It's equal to minus 6i plus j. All right. Okay. So maybe that wasn't that impressive, right, with this 2 variable function, because maybe you figured that out instantaneously very easily. But what if I gave you a surface, right? The surface z equals x squared plus y squared, right? So this is a paraboloid. And I ask you, well, I'm interested in that point on the paraboloid. What's the normal direction? Or what's a normal direction? Again, there's one in the opposite direction. Okay, not so easy to figure out perhaps, but convert this guy to a function, gradient of it, right, is going to be this guy right there, or the opposite direction. We will be using this in the very near future. Okay, in the very, very near future, actually next week when we talk about Lagrange multipliers. Okay, so this is a major, major application of the gradient. Okay, otherwise, in terms of just computing the gradient, computing directional derivatives, hopefully that stuff is relatively straightforward. Just brutal calculation, just use the formula, right? Just have to remember du f is equal to gradient f dot u. But again, it's not just a formula, it's how we interpret this formula that's really, really useful for us in this class. Okay, so that'll be it for this week. Next week, we'll start to do some applications of this multivariable stuff. The most important ones being the ones having to do with optimization, because again, optimization runs the real world.